Okay, so we're just continuing to do our backwards pass, filling in our late finish times and late start times. Okay, so we finished up on E, so we're going to move down to D. Okay, so 21 comes down. Okay, and 21 minus 10, that's 11. Okay, and then F comes from the end, so 28. Okay, and 28 minus 4 is 4. Okay, so now we're going to, so let's do C first. Okay, so C, here we've run into a similar problem that we encountered during our forward pass, right? The fact that there are 2 subsequent events to C. Okay, so which of these latest start times becomes the latest finish time for C? Okay? Well, it's similar to how we did it before. Okay, so in order for, so D requires C. Okay, but if, so let's say that this 24 became our late finish time for C. Okay, so the latest that C finished was on the 24th day. Well, if that's the case, okay, then D, we've already said that the latest D can start, the latest it can start is the 11th day. But if C doesn't finish until the 24th day, then D is delayed, okay, which sets the whole project back. Okay, so similar to what we did with our forward pass, but because we're going backwards, we're going to sort of do the opposite. So in our forward pass, we took the maximum. Okay, in our backwards pass, we're going to take the minimum value. So this 11 is what's going to become our late finish time, okay, rather than this 24. Okay, so 11 minus 3 becomes 8. Okay, similarly up here we have a 15 and we have a 12, so we're going to take the minimum, which is our 12. Okay, 12 minus 6 is 6. Okay, and once again we have 6 and an 8, so we're going to take the minimum, which is the 6. That's going to go here. And 6 minus 6 is 0. And we can write zeros and 0 here like we did at the end, but it's not a huge deal. Okay, and so we are pretty much almost done filling in our empty spaces. We only have one more left, and that is this S, and we said S stands for slack. So slack is the difference between the late start time and the early finish start time, or the late finish and the early finish. So this minus this, or this minus this. Okay, no matter which one you do, okay, you're always going to get the same result. Right? So it's always the bottom minus the top. Okay? But in terms of a definition of what slack is, okay, so slack is sort of how much time or how much extra time there is to play with. Okay? So if a particular activity has slack in it, then that means that that activity is not as important that it be completed on time compared to an activity that would have 0 slack. So an activity that has 0 slack, okay, must be completed on time because there's no extra time allotted to that. Okay? And so when we're trying to find our critical path is the path of activities that must be completed on time to making sure that the project is done on time. Okay, so following that reasoning, then our critical path is going to be made up of the path of activities that all have 0 slack. Okay, so let's go along and find our slack for each term. Okay, so 0 minus 0 or 6 minus 6. Okay, this is going to have a slack of 0. I'll put that in blue. Okay, so 6 minus 8 or 11 minus 12. Okay, no matter which way you slice it, that is 2. Okay, so 6 minus 6 for B. Okay. 0. Okay. 24 minus 9, that is 15. Okay. 11 minus 9, that's 2. Okay. 15 minus 12 is 3. 12 minus 12 is 0. 21 minus 19 is 2. 20 minus 20 is 0. 24 minus 24 is 0. Okay. Alright, so we've calculated our slack. Okay. So we can see that we have 0 slack here for A, for B, for H, for I, and for J. Okay. These activities with 0 slack make up our critical path. Okay, so these are the activities that it is extremely important that they be done on time, okay, or else the project will not finish on schedule. Okay, so we can write that down. Okay. So a critical path is A, B, H, I, J. Okay, so that makes up our critical path, those 5 events. Alright, so there is one final thing that we have to do. Okay, so if we want to calculate probabilities, okay, in particular the assignment that you were given asks for probabilities, different probabilities depending on the scenario that you have, right? But for instance, let's say that the question asks, well, what is the probability that the project is completed in 27 days? Okay, this 28, okay, is not the be-all and end-all really, because how was this 28 calculated? This 28 was calculated using these duration times. Okay? But they weren't true duration times. We used the expected times, right, which was an average based on optimistic and pessimistic times as well. So what this 28 is this 28 is actually the average, the mean completion time. So really there's a 50-50 chance, or a 50% chance, that the project will be completed in 28 days or less. Okay, and a 50% chance that it will take longer than 28 days, sorry. Okay, so we can ask, well, what is the probability of this being completed in under 27 days rather than in under 28? Okay. Well, we assume that the completion times are normally distributed. Okay, so in order to find probabilities using the normal distribution, if you remember, we needed two things. Okay? We needed the mean and we needed the standard deviation. Well, the mean, we're going to use this value. This 28 becomes your mean. Okay? And we use the mean and the standard deviation to convert to a z-score, which we would then look up in the table in our book. Okay? So the only other quantity that we need is our standard deviation. So if you read the package that you were given, okay, it gave you a formula for the variance. Okay? And so that formula, okay, let's scroll way back up to here, okay, to our table, okay, looks like this. Okay? So remember that sigma squared is our notation for variance. Okay? So we have P minus O, so P is the pessimistic time, O is the optimistic time. Okay, so pessimistic minus optimistic divided by 6 all squared is going to be an approximation for our variance. Okay, so what pessimistic time and what optimistic time are we using, because we have whole columns of them? Well, really, what we're going to do is we are going to find the variance for each activity in the critical path. Okay, so we're not even going to bother, right, calculating the variance for activities that aren't in the critical path, because the reason is the activities that are not in the critical path, we don't care how they vary, because they're not important. They're not as important to the project completing on time as the activities in the critical path are. Okay, so we'll start with activity A. Okay, so activity A becomes the pessimistic, which is 12, minus the optimistic, which is 4. Okay. And when we do that, let's install the superscript. We end up with 1.78, okay, as our variance. Okay, so I will ask you to pause here briefly and calculate the variance for the other activities in the critical path. Okay, so our variances become 1.78 for A, 4 for B, 2.78 for H, 0.11 for I, and 0.44 for J. Okay? But really what we are concerned with is the total variance for the critical path, and that is just the sum. So when we add those all up, we get our total variance. Okay? Total variance. Oops. Okay, of 9.11. Okay, but to use the normal distribution, we don't want the variance, we want the standard deviation. So if you remember how we get the standard deviation from the variance, well, the variance is sigma squared, and the symbol for standard deviation was just sigma, so we take the square root of the variance, okay, to get our standard deviation, and if we do that, we end up with 3.02. So when the question is asking us questions about probabilities, okay, we're using our normal distribution, so we need our mu and our sigma to calculate z-scores. Okay, so our mu, our average, is going to be 28 that we calculated for our project length, and then our standard deviation is the square root of the variance of the critical path, which in this case is 3.02.